Let's discuss a very important concept. It's a very simple one. The name of the concept is Theorem of Geometric Mean. Now when you look at this title, look at those two words, geometric mean, and you'll think, what do we mean by geometric mean? What is the meaning of this? It's going to be very easy. Let's understand that. Then we'll go on to the statement of the theorem, right? So let me give you an example for this. If I say that B is the geometric mean of A and C, then this means that B square is equal to A into C. That's the meaning of this. I repeat, when we say that B is the geometric mean of A and C, that means that B square, that means square of B, is equal to product of A and C. That is what it means. That means if I say X is the geometric mean of Y and Z, that means X square is equal to Y into Z. That is what it means. Beautiful. This idea is so simple, right? I'll tell you from where this concept originates. This originates from the concept of continued proportion. Now when we say proportion, we know when two ratios are equal, they are said to be in proportion. That means if A upon B is equal to B upon C, now two ratios are equal, they are in proportion, right? Now here B and B, they are same. A upon B equal to B upon C. That means we say A, B and C are in continued proportion. And then when we multiply, cross multiply that, what do we get? B into B is B square is equal to A into C. That's the concept. So when we say B square is equal to A into C, that means what? B is the geometric mean of A and C. That is what you have to understand. Okay. Now let's see the statement of the theorem. Right? Now it's going to be easy because you know what do we mean by geometric mean, right? Now from this statement, let's first understand what are we supposed to draw. It says that in a right angle triangle, that means again this theorem is applicable only in a right angle triangle. So we have a right angle triangle here, ABC. Yes, it is a right angle triangle. It says a perpendicular segment to the hypotenuse. Now what's the hypotenuse here? It is AC, and there's a perpendicular dropped on the hypotenuse. That means it is from B, and that is BD is the perpendicular on AC. It says that. What happens then? Then what it says is, observe the perpendicular segment to the hypotenuse from the opposite vertex. That means from B. We are talking about which segment? Perpendicular segment, that is BD. It says that this BD is the geometric mean. They are saying that BD is the geometric mean of the segments into which the hypotenuse is divided. Now let's understand. BD is the geometric mean of what? Of the segments into which the hypotenuse is divided. Now because of this perpendicular, the hypotenuse is divided into two segments, isn't it? One is AD, the other one is DC. They are saying that this segment is a perpendicular, this segment is the geometric mean of AD and DC, AD and DC. So when I say that BD is the geometric mean of AD and DC, what do you mean by that? We have already understood. BD is the geometric mean of AD and DC. That means BD square is equal to AD into DC, and that is what the theorem says. So let's first understand, this theorem is going to be applicable in a right angle triangle when there is a perpendicular drawn on the hypotenuse, and when we get that, the result is going to be BD square is equal to AD into DC. That's the way we're going to present it. That means when we apply this in any sum, we're going to write first in triangle ABC, angle ABC is equal to 90 degree. That means first we said it is a right angle triangle. Then we say that there's a perpendicular on the hypotenuse, which we wrote here. Hence we get BD square is equal to AD into DC, and we write the reason into bracket there as theorem of geometric mean. So one thing is clear, this theorem is applicable only in a right angle triangle whenever there's a perpendicular dropped on the hypotenuse. Beautiful. And hence we get that BD square is equal to AD into DC. Isn't that easy? Very simple, right? Now let's understand how do we prove this theorem. So obviously for proving this we require a right angle triangle. We have a right angle triangle. There should be a perpendicular from this Q on the hypotenuse. We have that. So let's first write that in the given. So we write that in triangle PQR, angle PQR is equal to 90 degree. Then we have segment QS perpendicular to hypotenuse PR. What are we supposed to prove? We need to prove that this perpendicular segment is the geometric mean of PS and SR. That means QS square is equal to PS into SR. That is what we need to prove. Okay, beautiful. So now we have understood what we are supposed to draw, what is the given and what is the to prove. Now let's think about the proof. The proof is going to be very easy. Now one thing we learned, that whenever there is a right angle triangle and there is a perpendicular dropped on the hypotenuse, we get three triangles, two smaller triangles and the bigger one, and all the three triangles are always going to be similar. Beautiful. Why? Because of similarity of right angle triangle. Let's choose that. So first, how do we write? In triangle PQR, angle PQR is equal to 90 degrees. Next step we write, segment QS is perpendicular to hypotenuse PR. So what happens? All the three triangles similar. We learned the trick. How do we write it? First write the name of the bigger triangle with 90 degree in between. So we write it as triangle PQR. Now the name of the next one. Pick up this point S, right? Write it between the first two letters. That means between P and Q. So what do we get? Triangle PSQ. So that's the second triangle. Pick up that letter, write it between place it between Q and R. So what do we get? Triangle QSR. We wrote that. Beautiful. And what's the reason for this? The reason is theorem of similarity of right angle triangle. And that's our result number 1. We wrote that. Beautiful. Was that easy? Now why did we do that? Now we know that if we have such a condition, we know this is the theorem which we apply. We want product equal to product. And we know that product equal to product, that means we want triangles to be similar, which we already have. Now the question is, to get this product, which pair of triangle should we consider? I'll tell you, it's very easy, very simple. Observe, we want QS square. QS square, that means we want that QS 2 times. That means we require 2 triangles which contain QS. Now look at this triangles and tell me 2 triangles which contain QS. Tell me, 1, QS is here. Yes, tell me the next triangle which has QS. Yes, that means the 2 triangles which we are going to consider is going to be triangle PSQ and triangle QSR. Beautiful. These are the 2 triangles. And we know it is similar. We know it is similar from 1. We just write them similar. Right? We picked it up. Why? Because we want QS square. So take the ratios which involve QS. So here we have QS, yes, so its corresponding is PS. So what do we write? We write PS upon QS. So we write there PS upon QS. That is equal to. Next one, what is the next one? Next QS is here, observe, yes. So its corresponding side here is SR. So we write QS upon SR. Beautiful. And what is the reason for that? The reason is nothing but corresponding sides of similar triangles. We write it as CSST. Beautiful, we wrote that. What next? Just cross multiply. So when we cross multiply, what do we get? QS into QS. How much is that? QS square. We write QS square equal to PS into SR. We write equal to PS into SR. And that is nothing but the proof. We got the proof. Was that easy? Very easy, right? So remember, in any right angle triangle, whenever there's a perpendicular dropped on the hypotenuse, we have 2 things. We can get all the 3 triangles to be similar, which we have already learnt. And we learned that there is one more thing which can happen is, right, that is this perpendicular segment will be the geometric mean of the segments into which the hypotenuse is divided. That means QS square is equal to PS into SR. But when we use that, we write the reason as theorem of geometric mean. Was that easy? Very easy, right?
And yes, please do not forget to like, share, subscribe and press the bell icon.